Talk about slope.
Oh, so this is how it goes?
Yeah. So slope, if you think about like a mountain slope is because it's got like it's steep, right? And steep is like an angle. If you have something that's relatively flat, it's not steep. If you have something that comes up straight up and down, it's really steep.
Like hills.
Yeah, hills, mountains, cliffs, they're steep.
They like
Yeah, so like just if we talk about, I'm just going to draw something right here. Like if I say I have a mountain, it's steep. If I have a hill, it's not so steep. If I have Florida, it's not steep at all, right? So steepness has to do with like an angle of elevation. So lines have that kind of angle of elevation also, and that's called their slope. So what we do is, I'm going to erase my mountains in Florida.
Why is your screen going disco?
Because it's recording. That's okay. So what we have is a way to measure the steepness of a line. And the steepness of the line is how far you've gone up versus how far you've gone over. And that's rise for going up and run for going like sideways. And the way I like to think of it to remember which one you have to do on top, you have to rise before you can go running. Right? Like you can't like be laying down and be running. You have to get up and then you go run. So you rise first before you run. So that comes on top. So hopefully that'll help. And the rise is the difference in the y values because it's up and down, and y moves up and down. And the x is the difference in the run is the difference in the x's because x's move side to side. Okay, so I'm kind of working this backwards. So the change in the y's over top of the numerical change, these are numbers, gives us the slope. So we can subtract any two y's and the same two x's. Like, so if I have a point here, I'm going to call these, well, I have x and y, but how do I know which is which, right? So we give them what's called a subset. Whoops. X1, Y1, X2, Y2, 2. So that's what these numbers are here. These are subsets, and subsets are not like an exponent. You don't do anything with them, they just tell you this is the second y minus the first y. This is the second x minus the first x. And now if I have these 2 points, it's arbitrary. For right now, I call these ones and these twos. Eraser. Pen. Giant. Sorry. Giant eraser. Thank you. Sometimes I get in the way. So I could easily call this x2, y2, and I could call this x1, y1. It doesn't matter which one, like which point are the ones and which point are the twos. You just can't say this is x1, y2. They have to both be ones or both be twos. So far, okay?
This might be a stupid question.
No.
Okay, so whenever we talk about it, we talk about rise over run. Okay, and then when we read that, x y2 minus y1 divided by x2 y. So why would we write it in sets and in notations? Do we put x first?
Oh, you mean like in the coordinate type?
Like yeah, when we're coordinating.
Because it's alphabetical.
Well, I'm just saying, why was it not called the x-axis and the y-axis? What, you know what I mean?
Yeah, no, that was just.
When we work it,
talk about, like, when we get to distance formula, the x comes first. So it's sort of, they did this to be alphabetical. And so then if I use any two letters at all, I can use any two. It doesn't have to be x and y. I can use any two letters as long as they're alphabetical. That tells me that this axis is the first one in our axis. So like if I use A and Q, it would go A, Q, because they're alphabetical. And that's just why they do it. They do it alphabetical so that it's the same no matter what letters we're using. That's why the x comes first. Then
Yeah, I know, I realize that. I'm just saying, why didn't they call? That's why I was saying. I was just asking why they didn't call the y-axis the x-axis, the x-axis the y-axis. So.
Well, okay. Here's why. The x-axis is one-dimensional, and it came first. The y-axis adds 2 dimensions. It came second. And then we have what's called the z-axis, which if I had like a pole that went straight into the middle of this point, that would be the z-axis that adds 3rd dimension. So that came last. So that's why they're in the order they're in.
Is this permanent?
Yeah.
Like, is it always like that?
Now they can rotate in real life, like in reality.
Like upside down?
Yeah.
But they still stay.
But they still say one is x, one is y, one is z.
Depending on how you write it down. So even if you like flip it this way, a certain axis can become another.
Yeah, we could rotate it and make this y and this x, but then we'd graph it all differently. And then that would change the formulas and stuff. So standard way of doing it is to have x be horizontal and y be vertical. That's just so that everybody sees it the same way and everybody's doing it the same way. It's just people made rules so that everywhere you go, the math is the same. Math is the only truly universal language. Okay, so let's say that the points these that we're given are 5, -1, and 7, -9. Now the 5s and 7 are blue because they're x's, and the 1 and the -1 and -9 are red because they're y's, and I wanted to make sure that you knew that the x's go together and the y's go together, so that there's no confusion. So what we want to do is, do you want this point to be x1, the 5, or the 7 to be x1?
The first one to be x1.
Okay. So that would be x1, y1, and this will be x2, y2. And again, that's completely, it doesn't matter. You'll get the same answer either way, so long as both of them are 1s and the other two set are both 2s. Okay, so then we're going to use the slope. Now, m is the symbol for slope, which they couldn't use s because s is for speed. And m stands for magnitude, and magnitude and steepness are the same kind of idea. So that's where the m comes from, is magnitude. So I've got the formula, y2 minus y1 divided by x2 minus x1. So now I'm going to plug these numbers in. y2 is -9 minus y1, which is -1, divided by x2, which is 7, minus x1, which is 5. Now my negative minus a negative
This is positive.
is positive because he's happy. So I get -9 plus 1 divided by 2. And -9 plus 1 is -8 divided by 2. And -8 divided by 2 is -4. And so that has given me my slope. My slope is just -4 in this case.
-4 is your slope, right?
Yeah, -4.
Roosevelt versus Obama.
Okay, we're going to do the slope of the line passing through 1, -2, and 4, -11. So we want to make these x1, y1, x2, y2. Okay? And that's arbitrary. I could have made the other ones x1 and y1 and vice versa. It really, honestly, doesn't matter which is which, just so long as they're both ones and both twos. I'm going to say that like 500 times. You get sick of it. All right, so my slope, y2 is negative 11, minus y1, which is negative 2, over x2, which is 4, minus x1, which is 1.
Does it always go like that, backwards?
It depends on how you set it up. If I had said the first point was x2, y2, so let's, you know what? That's a good experiment. Okay, so let's say we did this. And I said that this was x2, y2, and this was x1, y1. And we'll work it out that way after we're done working it out this way. Okay? So right now that we're here, negative minus, so that becomes plus 2. 4 minus 1 is 3. Negative 11 plus 2 is negative 9 over 3. So my slope is negative 3. Now what if I had switched the points? Same formula, but now I've got them backwards, right? Because I put the other point first. So I'm going to get negative 2 plus 11 over negative 3, which is going to give me 9 divided by negative 3. So it's the same. The only thing, it doesn't matter which set of points is the ones and which set of points is the 2. The only thing that you cannot mess up
Is the way you
can't put a 1, 2 in the same parentheses.
Right.
Because I can't say like negative 11 minus negative 2 over 1 minus 4. They have to go, that point, if 4 negative 11 comes first, it has to come first on both. The top and the bottom, do you see what I mean? So if negative 11 came in front, then 4 has to come in front. You can't flip the order. Yeah.
By switching them around, is that a way that people can check to make sure the answer is correct?
Yeah, you could do that. Also, sometimes putting 1 point in the front makes the subtraction easier. Just depends. Like if for example, let's say I might make these 3 and the 6 my x2, y2 because they're larger than 1 and 2, and so then I'm just subtracting instead of dealing with negatives. So it's really a matter of preference. Yeah, it's a matter of preference. Or in my case, what I always do is I always personally just whatever point came first, those are my 1s. Whatever point came second, those are my 2s, just because that's easier for me. But it's really, it doesn't matter as long as they're both 1s and both 2s. So you can make either one, the 1s and the 2s. You just can't mix the 1s and the 2s together. Does that make sense? All right, so let's try a couple. I'm going to pause the recording, let you guys work on them. Rate of change is really applied slope. And by applied slope, I mean it's a slope of a line or, you know, whatever that is associated with items. So like when we did on the test, we had the mango function. So the rate of change would be how the price of the mangoes increases versus how many mangoes you buy. That would be the rate of change. So here we have computer games versus their cost, floor tiles versus the area that they cover. And that's what rate of change is. It's slope, but it's slope that the numbers are applied to items, things, money, size, numbers of things, you know, just, it's applied. Does that help make sense of rate of change versus slope? I mean, they're the same thing, it's just rate of change is applied.
What do you mean by
Slope is of any line anywhere, just any points on X and Y graph.
Like how we can use any one, it doesn't matter.
Yeah, well, slope can be any X and any Y. Rate of change is X's and Y's associated with specific stuff.
Okay.
Slope is just general, rate of change is specific. Yeah. So we talk about the rate of change and, you know, like, you could talk about like college enrollment, year versus year versus year. That would be a rate of change. So it's an applied thing. It's specific to a certain item or topic or number as opposed to just random numbers. Does that make sense? So what we can do, there's two ways to do this. We can use the slope formula, the y2 to y1, x2, x1, which I think is the best way to do it because that keeps us in the same area. Or we can do some other stuff, but I'm going to use the slope formula first. So remembering that slope if I have to pick 2 points, I can use any two. I can use the first two, I can use the second two, I can use the first and the last. Which one would you like to use? First two. Okay, so we'll call this x1 and x2. And we'll call this y1 and y2. Okay? And like I said, I could use any 2 points. Yeah, because it should be a constant rate of change. It should be anyway. So y2 minus y1 over x2 minus x1. And 156 minus 78 is 78. 4 minus 2 is 2. So that's 39. Okay, so my slope is 39. And what does that mean? Well, if I have 2 video games are $78, 4 video games are $156, 6 video games are $234. But to go up each time, so if I said 3 video games, I'd add 39 to the y. Because it's saying the 39 is, the y is increasing by 39 with each x. So each game adds $39. That's what the rate of change is. Okay. Which 2 points would you like to be using on the second example? For which I'm switching to green. That one or this one? So do we want the first two, the second two, the first and the last?
First and last.
We'll do, okay, first and last. So that's x1, x2, y1, y2. Again, you can pick any 2 points, just make sure that if this is a 1, this is a 1, if this is a 2, this is a 2. Okay, so I'm going to plug them into the formula. So 48, nope, sorry. I have 144 minus 48 over 9 minus 3, which 144 minus 44 is 100, minus 4 is 96, 9 minus 3 is 6, and 6 goes into 96 16 times. So my rate of change is 16. I didn't say what the area of the tiled surface is. I'm just going to say they're square inches maybe, because I didn't say, so we'll just say square inches just to be arbitrary. So what this means is that each tile so every tile would add 16 square inches to the area that's being tiled. Because as we add each tile, we're getting 16 more square inches. Yeah.
How come it doesn't matter which one we do? Like, like on the first one, we did x1 and x2 for 2 and 4.
Mm-hmm.
How come it doesn't matter if we do 4 and 6 or 156 and 234?
The difference between 156 and 78 is 78. The difference between 234 and 156 is 78.
Is it always going to be like that?
Not always. We're going to talk about that in a second. Here I've got 2 and again 2. And that's why I can use any points, because the space between them is the same. Yeah.
Okay, this is probably one of my biggest challenges, the reason why I'm not doing this. Why wouldn't I just divide 3 to 48 in 16? Or 6 into 96?
But sometimes we get a slope using these points. But if we're talking about an equation right now, this would be 3 equals 16, or y equals 16x. But sometimes we get equations where the slope would be like 16x plus 5, so you wouldn't be able to do a straight division.
Okay, so we're just breaking this down. Okay.
Yeah, we're just breaking it down into parts, and then we'll build.
Okay, I got you.
Remember I said I'm going to try to break it down a whole lot? So, yes, for these examples, yeah, you could do that, and it would work. But for future examples, it won't. So we want to use the slope formula just to make sure. Good? We have rate of change that's not constant. And that's when you have a variable rate of change. Okay, if our rate of change is not constant, that's when it's variable. So if we look at this graph shows the number of people who visited has an S in the middle of it, U.S. theme parks in recent years, and these are in millions. I accidentally got that cut off when I copied this over. So it's in millions. So in 2000, if we look at this is 20, 19, 18, 17. So 317 million people came. In 2002, I have 20, 21, 22, 23, 24. 324 million people went to the amusement parks. In 2004, it went up to 325 million people visiting theme parks. And in 2006, it's up here at 335 million. Okay. Now, as you can see though, the change is not the same all the time. Rate of change is constant, goes up the same amount each number. But we are going up from 317 to 324 between 2000 and 2002, but between 2002 and 2004 we only went 1. So we're not going up the same amount every time. So if we find the rate of change for 2000 to 2002, I will do 324 minus 317 over 2002 minus 2000, so over 2. Because 2 years have passed, right? 24 minus 17 is 7?
Yes.
7, yeah, 7. And I'm going to break this down because we're talking about rate of change, and so I like to do it in terms of per 1 year. So between 2000 and 2002, 3.5 is my rate of change. Okay, then if I do 2002 to 2004, I have 325 minus 324. Again, that's a 2-year difference. So that's 1 over 2, so that's 0.5. Okay, what's the meaning? Well, between 2000 to 2002, we have 3.5 million more visitors per year. Between 02 and 04, we only have 500,000. So the increasing number of people that go to the park every year, it went down. Okay. And then to answer the last question, how are the rates of change shown on the graph? See how steep this line is? And then you have flat, and then you have really steep again. So it's shown by the steepness of the line. Now, our book doesn't go over this, but I'm going to tell you about it anyway. And we can find something called average rate of change. Okay. Oh wait, oops, I have to actually select the color for it to work. To find the average rate of change, you do the last y minus the first y over the last x minus the first x. So in this case, it would be 335 minus 317 over 2006 minus 2000. Okay, 17 to 20 is 3, and then another 15, so 18 over 6. So the average would be 3 million a year. Average rate of change is really good in business applications because it tells you your pattern of growth or your pattern of decline. Because it gives you an average rather than saying, well, this year we did this much, and that year we did this much, and this year we did that much. It gives you a general idea of the whole thing, the whole picture. It's a big picture idea. Linear versus nonlinear. If we have a constant rate of change, let's go back to our mangoes. If we had 3 mangoes, they were $5, 6 mangoes was $10, 9 mangoes was $15 or whatever. There's a constant rate of change, right? It's going up the same amount every time. That's going to give us a straight line if we were to graph it and actually connect the dots.
But we're not gonna.
Not in that part. Now, a variable rate of change, that's like we just saw with the amusement parks, wasn't a straight line, right? It was a jagged line. So that's linear versus nonlinear. So to tell if a function is linear or not, we're going to see if the rate of change remains the same throughout the data. Okay, so what we want to do is we're going to take our y's. To go from a -6 to a -8, I subtract 2. To go from a -8 to a -10, I subtract 2. To go from a -10 to a -12, I subtract 2. To go from a -12 to a -14, I subtract 2. Now I check my x's. To go from a 1 to a 4, I add 3. 4 to 7, add 3. 7 to 10, add 3. 10 to 13, add 3. They all match. If they all match, we have a constant rate of change, so we are linear. Okay. We come over here. To go from 10 to 12, I add 2. I add 4. I add 2. I add 4. Now, I am not going to decide whether they're linear or not yet until I check the x's. Because let's say, okay, to go from a -3 to a -1, I add 2. Well, if I add 4 on the next one, then it'll be okay. But I'm adding 2. As soon as I see that this doesn't double the way that that doubled, then I know it's not linear. And then we come over here, and we say pattern doesn't follow. Can you guys see the green?
Yep. How do you not just want to draw stuff?
Oh, I do.
Kudos for you for teaching, but I just be drawing individually.
So if these don't match, but this pattern is the same, then it's okay. Right? But if these don't match and this pattern doesn't follow, it's not a constant rate of change, so it's not linear. So if this went plus 2 plus 4 plus 2 plus 4, or even if it went like plus 1 plus 2 plus 1 plus 2 and it doubled it like this one did, we'd be okay. So far okay? Guys, look at this one real quick. And just tell me, looking at these numbers, are these going to all match? 4, 4, 4, 1.
How do you, well, 1 and 1, no? Plus 1. Negative 1 plus 1 would be 0.
So I've got plus 4,
Plus
4, plus 4, plus 4, right? Those are all good. I'm going to have plus 1, plus 1,
plus 2.
plus 2, plus 1. That's going to make us not linear.
Trying to throw us for a loop with that negative 1.
Yes, I did. But does that make sense? I'm just looking at, to get from this number to this number, what do I have to add? Or subtract? Like if it was going down, I would subtract. Okay, so from here, want to try this one? So negative 4 to positive 1.
5.
1 to 6.
5.
6 to 11.
5.
11 to 16.
5.
So we're good.
Yep.
12 to 9.
3.
Minus 3. 9 to 6.
Yep. Negative 3. Negative 3. Negative 3.
They're good. So we're linear. Not too bad.
Fun with numbers.
Okay, I want one more thing. It's going to take just a little bit. I just want to show you what the slopes look like. Okay, so if we have a positive, it goes up. As you move from left to right, like you're reading a book, it'll move up. If we have a negative, it moves down. 0 slope is flat. That's not flat. Oops, that's not the right arrow.
What if it's a vertical?
Huh? Oh, that's why. I can't make a flat line apparently. Flat. And then if I have undefined, is straight up and down. Okay.